We are in Rosen, Discrete Mathematics and its Application, section 8.3 on divide and conquer algorithms and their recurrence relations. And we take a look at Theorem 2 in the chapter it's called the Master Theorem, because it allows us to analyze a greater variety of divide and conquer recurrence relations than Theorem 1 does, which had the limitation that the conquer portion was dictated by a constant. Here, for the master theorem, we will have the conquer portion be a power of n times c, but everything else in the divide and conquer relation will stay the same. And we'll see that with the master theorem, we can analyze, there's three different possibilities where my number of subproblems is less than b raised to the d power, whether it's equal to b raised to the d power, and whether it's greater than b raised to the d power. And we get big O of n to the d, big O of n to the d log n, big O of log base b of a for each of those cases respectively. So let's look at a proof of this theorem, because it is important to know when we can apply it and what big O certain divide and conquer algorithms will have. All right, so again, we're using c times n to the d for my conquer function, and we will continue to make the simplifying assumption that n is a power of b. And earlier we had shown that the divide and conquer relation, when addressed iteratively, gives us this function with a to the k times the initial condition plus this sum j equals 0 to k minus 1, a to the j, and g evaluated at smaller and smaller arguments as b to the j, as j goes up for b. All right, well, we can substitute for this with our known function, and c, this c inside will just factor out, and this argument here will simply be raised to the d power inside the sum. And this n to the d is not related to our index, so it can come out. So I have c times n to the d out in front of the sum. And then I'll put a over b to the d, and then then that ratio will be raised to the j power. So here's a to the j, b to the j. I bring b to the d into the denominator, a into the numerator, and then j will be the exponent in the sum. Everything else stays the same, a to the k and times the initial condition. Now, we'll check our cases. First case will be when a is equal to b to the d. Well, in that case, the argument for my exponent is just going to be 1, and I'm going to be summing up c times n to the d k times, so I'm missing a plus there. And recall that a to the k is equal to n log base b of a from the earlier proof. And then since a is equal to b to the d, n to the log base b of a is just n to the d. And k is equal to log base b of n. And so the dominating term will be c n to the d log b of n. So when a is equal to b to the d, I get big O of n to the d log base b of n. Okay, well, now how about the other two cases? We'll tackle them with a single case. A is not equal to b to the d, and then we'll break it down to see which term dominates. All right, when a is not equal to b to the d, we don't have quite so simple a sum, but we do have a truncated geometric sum right here. So I can apply our formula, which is will be the argument raised to the k power minus 1, when k minus 1 is my upper range, over the ratio a over b to the d minus 1. All right, that's just straightforward application of our formula. Now I'm going to multiply both sides, the top and the bottom, by b to the d, so a form of 1. And I note that b to the d to the k is just n to the d, because b to the k is n, leaving d as my exponent. And I'll multiply through the b to the d's. Here's my n to the d here, and now you can see that every term has b to the d multiplied by it, or in this case it got canceled out. Now I'm going to substitute this expression here for that sum back into 1, and I get my function in n is a to the k times my initial condition, c times n to the d times this expression for the sum. And now I'll multiply through. Note I have a to the k in 2 places, so we'll want to combine terms there. This n to the d will cancel that n to the d, but it will get multiplied over here like that. So combining, and also remember that a to the k is equal to n log base b of a. So combining terms for that, I get my initial condition, and then c times this term here, b to the d over a minus b to the d. Now for this term here, my n to the d gets multiplied by this b to the d. So this n to the d comes here. C gets multiplied by b to the d. And I change this negative to a positive by reversing the direction of the subtraction in the denominator. And now I have a function in 2 terms. F of n is equal n to the log base b of a times a constant, and n to the d plus n to the d times a constant. Which one will dominate? Well, when a is greater than b to the d, then n to the log base b of a will dominate n to the d, because log base b of a will be greater than d. If I take the log of both sides of that inequality, I'll see that. And of course, if a is less than b to the d, then n to the d will dominate n log base b of a, because log base b of a will be less than d, and we'll see that if we take the log of both sides of that. So in the first case, my Fn is big O of the dominating factor, n log base b of a. And in the second case, it's dominated by n to the d, so it's big O of n to the d. And that concludes the proof for Theorem 2.